At the beginning of this class, we looked at the very simple equation y prime equals a times y, with an initial condition y of 0 equals y sub 0. Now we recognize that the derivative of y was just a constant times itself, and so it must be that y is an exponential function. In fact, we saw that y of t is equal to y naught e to the at. Later, we moved on to systems, where y prime is a vector, and that equals a times y, where a is a matrix and y is a vector. Again, we have an initial condition that y of 0 equals y naught, where y naught is a vector. Couldn't we just say that y of t is equal to e to the at, where a is a matrix, times the vector y0? Does that make sense? Well, let's see if we can figure that out. So we're going to move into some calculus and think about the series for e to the x. We used some derivatives to calculate the series for e to the x back in calculus 2, and that was 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. And we learned all about power series and tests for convergence, and we saw that this series converges for all x. Well, instead of taking derivatives to find the series, why don't we define e to the a as its Taylor series? So e to the a is going to be 1, or in this case, we'll call that the identity matrix, plus a plus 1/2 a squared plus 1 over 3 factorial a cubed plus 1 over 4 factorial a to the 4th, etc. Now, each component of this matrix is going to be a series for the exponential, and so each one of those series is going to converge, and therefore the series for e to the a is going to converge. Well, what happens if we try to take derivatives of something like e to the at? Well, the derivative of e to the at is going to be the derivative now of a series, the series I plus at plus 1/2 a squared t squared plus 1 over 3 factorial a cubed t cubed plus 1 over 4 factorial a to the 4th t to the 4th, etc. I'm going to take that derivative term by term. I'm going to think about the derivative as being the derivative of each component of the matrix. So for the identity matrix, I'm going to take the derivative of a bunch of constants, and that's going to be 0. And then the derivative of a times t is just going to be a. And the derivative of 1/2 a squared t squared, because the derivative of t squared is 2t, that's going to be a squared t. The next derivative is going to be 1 over 2 a cubed t squared, and the next derivative is going to be 1 over 3 factorial a to the 4th t cubed, etc. Let's see what happens when we factor out an a. I'm left with the identity plus a times t plus 1/2 a squared t squared plus 1 over 3 factorial a cubed t cubed. And that looks familiar. That looks like the series I just differentiated. In fact, what is left is a times e to the at. So if you take the derivative of e to the at, you get a times itself. Oh, well, that means that if I let y be e to the at y sub 0, then its derivative is going to be a times itself. And of course, e to the 0 is going to be the identity matrix, so y of 0 would be y sub 0. So now we see that the solution to e to the a, or dy dt equals a times y is e to the at times y sub 0. But now that I've solved that system, how do we actually calculate e to the at times y0? Well, let's think about diagonalizing matrices. Okay, let's go back to linear algebra. Okay, so A is going to be a matrix, and we're going to assume that A has eigenvectors, we'll call them v sub I, so that A times v sub I is lambda I v sub I. And we're going to assume for the moment that all of the eigenvectors are linearly independent so that we can diagonalize this matrix. So P is going to be a matrix whose columns is the eigenvectors of A. So when I form P, its columns are going to be v1, v2, all the way down to v sub n. Okay, so then what happens when you take A times P? So A times P is going to be A times the matrix v1, v2, all the way down to vn. And when you do matrix multiplication, right, that's actually going to give you that the first column of the product is going to be A times v1, and the next column is going to be A times v2, and that goes all the way down to A times vn. But because these are eigenvectors, A times v1 is lambda 1 v1, A times v2 is lambda 2 v2, and that goes all the way down to lambda n v sub n. Well, we can rewrite this as v1, v2, all the way down to vn, times a matrix that has the eigenvalues lambda 1, lambda 2, all the way down to lambda n on the diagonal. So A times P is actually equal to P times a matrix we'll call capital lambda, where lambda is a diagonal matrix with the eigenvalues on the diagonal. So since A times P is P times lambda, we could say that A is equal to P times capital lambda P inverse. Or we could say that capital lambda is equal to P inverse A times P. And that's how we diagonalized a matrix in linear algebra. Of course, this begs the question, is every matrix diagonalizable? Well, let's think of a matrix that maybe isn't diagonalizable. Let's come up with an example. Let's look at the matrix 1, 1, 0, 1. Lambda 1 equals 1 is a repeated eigenvalue in this case. And when you solve A minus I times V equals 0, then you get that the matrix A minus I is 0, 1, 0, 0. And the right-hand side is 0. And this tells you that the only eigenvector is actually 1, 0. There are no other eigenvectors. And so because we don't have two linearly independent eigenvectors, this matrix is not diagonalizable. So that'll be a special case that we'll have to watch out for later on. Now, a question might be, who cares about diagonalizing matrices? What's the point of that? Well, let's say you wanted to have to take large powers of matrices. So A we can write as P lambda P inverse. And so when you want to do A squared, you can do P lambda P inverse times P lambda P inverse. And that ends up being, let's see, P times P, or P inverse times P ends up being the identity. So that ends up being P times lambda squared times P inverse. Those inner two matrices multiply together become the identity, and so essentially cancel. But when I want to do a cubed, I'll have to do, let's do a, which is p lambda p inverse, and multiply that by a squared. So p lambda squared p inverse. Again, these inner two matrices cancel, and I'm going to get p times lambda cubed p inverse. Oops. Okay, so it looks like there's a nice pattern. When we want to take a to the nth power, we're going to get p lambda to the nth power p inverse. So why is that even important? Why do I care about powers of matrices? Well, remember that when we did the exponential of a matrix, e to the a was I plus a plus 1/2 a squared plus 1/3, 1 over 3 factorial, a cubed, etc. Well, I can think of as just being p times p inverse. And a, we know, is p lambda p inverse. We just calculated a squared as p lambda squared p inverse. And then, of course, a cubed we calculated as p lambda cubed p inverse. And that goes on. And you'll notice that in each one of these terms, we have a p on the left, and we have a p inverse on the right. So what I'm going to do is I'm going to factor out a p on the left. And then I'm going to factor out a p inverse on the right. And what I'm left with is the identity plus lambda plus 1/2 lambda squared plus 1 over 3 factorial lambda cubed, etc. And so I'm left with p times, well, what is sitting in these parentheses? In fact, what's sitting in these parentheses is e to the lambda, because that is a Taylor series for e to the lambda, and then p inverse. So if I want to calculate e to the a, I need to calculate p, the matrix of eigenvectors, and then I need to calculate e to the lambda and p inverse. Well, what about e to the lambda? How am I going to calculate e to the lambda? Well, let's see, what is e to the lambda? Well, that's going to be I plus lambda plus lambda squared, or sorry, 1/2 lambda squared plus 1 over 3 factorial lambda cubed, etc. Well, the identity matrix, well, that just looks like ones on the diagonal, zeros elsewhere. Lambda looks like lambda 1 on the diagonal, lambda 2 all the way down to lambda n on the diagonal, zeros elsewhere. Let's see, we're going to get, for lambda squared, so if you multiply two diagonal matrices, you're going to get another diagonal matrix. So you're going to get 1/2 lambda 1 squared on the diagonal, 1/2 lambda 2 squared, all the way down to 1/2 lambda n squared. And then the next term, lambda cubed, so if you multiply three diagonal matrices together, you're still going to get something that's diagonal. That's going to be 1 over 3 factorial lambda 1 to the n, 1 over 3 factorial lambda 2 to the n, all the way down to 1 over 3 factorial lambda n to the n. Ooh, I probably should have made my matrices not n by n. Sorry. I I wrote n's here, but I didn't really mean that. I meant lambda cubed. There we go. That's much better. Okay, and then there would be some more terms. Okay, so what does that look like? Okay, so let's put that whole big matrix together. So the first component, let me see if I can circle those. There's a 1, a lambda 1, 1/2 lambda 1 squared, 1/3 lambda 1, 1 over 3 factorial lambda 1 cubed. That's going to be 1 plus lambda 1 plus 1/2 lambda 1 squared plus, we're going to do 1 over 3 factorial lambda 1 cubed. Well, the next component's going to be, let's see, 1 plus lambda 2 plus 1/2 lambda 2 squared plus 1 over 3 factorial lambda 3 cubed. And those are going to go on forever. And then as I go down, the last component's going to be 1 plus 1 plus lambda n plus 1/2 lambda n squared plus 1/3 lambda n cubed plus, etc. So let's try to make this look a little bit more diagonal for you. Okay, so that's my matrix. And hopefully what you see is that each one of the terms in the diagonal is in fact, each one of the terms in the diagonal is in fact an exponential. Okay, so let's move that up there so that we can see what we're doing here. So this last matrix, e to the lambda, is going to be e to the lambda 1, because this first term here that you see is a Taylor series for e to the lambda 1. Okay, so the next term is going to be e to the lambda 2 on the diagonal all the way down to e to the lambda n on the diagonal. So calculating e to the lambda as a matrix is actually fairly simple. It's just e to each one of the eigenvalues. In the next video, we will look at solving an example.